Okay, Longhorns, we have another section on reviewing complex numbers, and I'm going to go over very quickly what a complex number is and some operations that we do with complex numbers. First of all, we have the imaginary unit I, and this is a complex number, part of the complex number that we have to use sometimes in mathematics to help us solve when we're trying to find the zeros of a function, or we're trying to find certain points in a polynomial that don't cross the x-axis. So when this happens, we use an imaginary number called I. So last year in Algebra 2, you learned that you cannot take the square root of a negative number, not in the real number system. Because of this, we use I, the imaginary number, to account for the negative. So I equals the square root of -1. Furthermore, we can add real numbers to this imaginary number to make a set of complex numbers, a number with the real and imaginary part. These numbers are written in the standard form a plus bi, where a is the real part and bi is the imaginary part. So the definition of a complex number is, if a and b are real numbers, the number a plus bi is a complex number, and it is said to be written in the standard form if b equals 0, the number a plus bi equals a, and is said to be a real number. If b does not equal 0, but a equals 0, the number a plus bi equals bi, and is called an imaginary number. A number of the form bi, where b does not equal 0, is also called a pure imaginary number. Equality of complex numbers. Two complex numbers and written in a standard form are equal to each other. A plus bi equals c plus di if and only if a equals c and b equals d. Addition and subtraction of complex numbers. To add or subtract complex number, you combine the real parts with the real parts and the imaginary parts with the imaginary parts. It's sort of like combining like terms. No, don't forget about the rules of addition and subtraction. Make sure to review terms as additive identity, additive inverse, associative property of addition and multiplication, etc. Okay, here's our first example. I'm going to go ahead and move the screen up and expand it. This is our first example for addition. It's very simple. It's just like when we add anything else, you're going to add only the like terms together. So here I have a 4 plus 1. 4 plus 1 is 5. And then I'm going to have a plus sign, and then I'm going to add the i's together. I have 7i minus 6i, and that's just 1i. But I'm just going to write I. I'm not going to write 1i. I'm just going to write I. And that's it. How simple is that? All right, so on the next page, before we can even begin looking at foiling for multiplying complex numbers, we need to review the pattern of values at which powers of I occur. So this is really important because if we have anything squared or to the third power or to the fourth power, the value for I changes. So let's take a look at this really quick. All right, so if I have I to the first power, that's just the same thing as the square root of -1, which we talked about just a minute ago. All right? And the resulting value for that is the number I. All right, so if we square I, what ends up happening is we end up having two of these root -1s multiplied together, and when we do that, the square root of -1 times the square root of -1 equals the square root of -1 squared, and we know that these two things are inverses and they cancel each other out. So what we're left with is this -1. So if you have an I squared, that's going to be the same thing as a -1. Now if I cube I, that's going to be the same thing as I to the first power times I to the second power, which is the same thing as I times a -1, because we already said that I to the second power is -1. So we end up with -I. So I to the third power is -I. The next one, I to the fourth power, this is where we would have two I squareds multiplied together. Well, we know that I squared is -1, so -1 times -1 is going to give us a +1. So let's review this really quick. I to the first power, I to the second power, -1. I to the third power, -I, and I to the fourth power, 1. This pattern repeats itself over and over. So all you need to do is take the power of I and divide by 4, because that's how many options we have here. We have 4 options. So if we divide our power by 4, you can then use this remainder, if any, to evaluate. So check out this remainder. If I have an I to the first power, my remainder is going to be 1/4, because if I divide 1 by 4, 1 divided by 4 right here, that's 1/4, or 0.25. So if my remainder on the number I get is 0.25, then my resulting value is I. If I have an I squared, then if I divide that by 4, 2 divided by 4 is 1/2, right here, 1/2, and that's 0.5. So if my remainder is 0.5 on my number, then my resulting value is -1 for I. I to the third, if I divide 3 by 4, that's 0.75. So if I have something that has a number that has a remainder of 0.75, then I have a -I. And I to the fourth, there's no remainder, the power is divisible by 4, that's just the number 1. So just remember, if there's no remainder, then the number you're going to get is the number 1. Okay, so let's try some examples. Find the value of I to the 54th power. All right, so all I have to do is take 54 and divide by 4. And I just pop that in my calculator, and I get 13.5. Okay, so the part of this I want to look at is this part right here, the remainder. Okay, I need to look to see, is that a 0.25? Is it a 0.5? Is it a 0.75, or is it a 0 if I don't have a remainder at all? Well, this is a remainder of 0.5. So if I look back to my chart, I'm going to look back up here to my chart, 0.5. If I get a 0.5 remainder, that means that my resulting value over here is -1. So if I get a 0.5, my resulting value is a -1. Therefore, I to the 54th equals -1. So I to the 54th equals -1. Let me write it down. I to the 54th power is the same thing as -1. Now you try. Find it, for the example, find the value of I to the 14th and find the value of I to the 103rd. So I'm going to let you do those two, and so when you show me your notes, I want to see that you've completed these two examples. Okay, now we're going to look at multiplication of complex numbers. Just remember your foiling rules and the value of I to different powers. Okay, so we're going to use those things we just learned in order to multiply two complex numbers together. And so we're going to use the same thing we use when we multiply two binomials together for quadratics, for example, and we're trying to get the standard form. This is kind of the same process, so we're going to just FOIL this. So let me make this bigger so you can see it better. Okay, so for example 1, we have 1 minus 6i times 4 plus 7i. And we're just going to use our FOIL. So we're going to do first times first. So first times first is 4. Then we're going to do our inside or outside times outside, which would be 1 times 7i. So I'm going to put a plus 7i. Then I'm going to do my negative 6, my inside. Inside times inside would be negative 6i times 4, which will give me negative 24i. I'm going to keep that negative sign, don't lose that. And then the last times last. Now this is where mistakes happen, believe it or not. Negative 6i times 7i. So what do we get here? I'm going to go ahead and write this out so you can see it. We're actually going to get a negative 6i times 7i. So I'm going to be really careful here because when I multiply these two i's together, I get I squared. So if you don't remember what I squared is, look back at that chart on the previous page. I squared is negative 1. So what we end up with here is really a negative 6 times 7 times a negative 1. Okay, so I broke this down a little bit. Normally I wouldn't break it down that much, but I want to make sure that you see this part because this is where mistakes happen because of all of these negatives. Okay, so negative 6 times a negative 1 is a positive 6. And a positive 6 times 7 is a positive 42. So this whole thing in green right here becomes positive 42. So now what I'm going to do is I'm going to combine all my like terms. I have these two like terms in the middle. These two like terms right here, I need to add those together. So what I'm going to end up with in the end is 4 plus, and then I have 7i minus 24i, which is 17i, but it's not positive. It's negative. So I need to change this to a negative. Okay, so be careful of that. When I combine these two numbers together, these two integers, 7 minus 24 is a negative 17, so I have to change that positive to a negative because it becomes a negative 17. And then I'm going to add my 42. Now another mistake I see a lot of times is students not writing this final answer correctly. The real part goes first. So I'm going to add the 4 and the 42, which is 46, and I'm going to put that number first. So my 46 is going to be the first part of my complex number answer. So 46, and then I'm going to have this minus 17i. So your final answer should always be two parts, unless of course a is 0. Then you're only going to have one part, but it should normally be two parts. You're going to have the real part, which in our case is this 46 right here. This is the real part, and the imaginary part, this part right here, which is our negative 17i. All right, so for an example 2, we actually have 3 of these complex numbers. I know it looks only like it's 2, but you need to be very careful of this first term. This one right here, this 2 minus 3i squared, when we get ready to work this problem, we need to break that apart into 2 separate complex numbers because this is 2 minus 3i times 2 minus 3i. We can't just multiply, or we can't just square 2 and then square 3i. We can't do that because that's not what this is. So we need to break it apart first. So don't forget this step, because if you try to do what I just said and try to square the 2 and then square the 3i, you're going to get the wrong answer. So we have to do this whenever we have one that looks like this. We have to break it into two separate complex numbers. Then we multiply that times 4 plus 5i. So I'm going to do this in little chunks. I'm going to do the first part, these first two first. I'm going to multiply these two together first, and then whatever the result I get from here should be another complex number, and then I'm going to multiply that complex number times this complex number. Okay, so let's take it in little chunks. Let's do this part first. Okay, so what I've done so far is I've multiplied just these two terms together, these two complex numbers. So I get 2 times 2 is 4, negative 3, or 2 times a negative 3i is negative 6i, negative 3i times 2 is negative 6i, and the negative 3 times a negative 3 is a positive 9, and I times I is negative 1. So I still end up with a negative 9 here. If you make a mistake, that's where it's going to happen, so watch out for that. You might want to do that calculation separately a couple of times until you get used to it. So negative 3 times negative 3 is a positive 9, but I times I is negative 1. So positive 9 times negative 1 is still negative 9. Then I just combine my terms. I get 4 minus 12i minus 9. 4 minus 9 is negative 5. And then I have my imaginary part, minus 12i. Now I'm going to multiply this imaginary number that I got as my result with the other imaginary number that's over here. So don't forget, you've still got this other imaginary number here that you need to multiply through. So I'm going to take this over here to the side, and I'm going to finish this problem. All right, so here we have negative 5 minus 12i times 4 plus 5i. I'm going to go ahead and multiply this through and get the resulting imaginary number. All right, so I've got a negative 20. Negative 5 times 4 is negative 20. Negative 5 times 5i is negative 25i. Negative 12 times 4 is negative 48i. And then I have the negative 12i times 5i, which is a negative 60i squared. And I went ahead and wrote it out like this to just break it down a little bit more for you so you don't get confused. This is a negative 60 times I squared. So if I squared is negative 1, then I have a negative 60 times a negative 1. That's going to give me a positive 60. So the sign changes. So like I said before, if a mistake is going to happen, it's going to happen right here. So watch out for that. Slow down, take your time, make sure that you've got the right value right here, whether it's positive or negative. So it's a negative 60 times a negative 1, which gives me a positive 60. Then I just combine my like terms, and I get 40 minus 73i. All right, so complex conjugates. This is a real important subject because something magical happens right here. The one thing you seem to always forget is that when we talk about imaginary numbers, especially as roots, they come in pairs. This is because in that plus or minus in the quadratic formula, if I give you a plus bi, then its complex conjugate is a minus bi. So if you kind of think about that difference of two squares thing, that might help you a little bit here. You want to have 1 plus, 1 minus. That's the same concept. So for example, multiply a plus bi by its complex conjugate. Your answer will yield something very important that is true whenever you multiply by the complex conjugate. So for this example, I'm going to multiply a plus bi times a minus bi. And I'm going to use FOIL just like we did before. I get a squared plus abi minus abi minus b squared I squared. All right, so when we simplify this, the two middle terms are going to cancel out. Plus ABI and minus ABI will cancel. And then I'm left with A squared. And then I have to simplify this part. And this is where we have to be very careful, because I squared, if you remember, I squared is -1. So what we have is a negative B squared times a -1. Well, negative B squared times -1 is just plus B squared. So we end up with A squared plus B squared. And this is the answer we're always going to get when we multiply a complex number by its conjugate. We're going to get this number here squared plus this number squared without the I. So we're always going to get A squared plus B squared. All right, let's do one more example. I'm going to do the short way and the long way. So first let's do the long way, and then we'll take a look at the short way. Okay, so I've done it the long way, which is just to multiply these two together. This is the complex number and its conjugate. So 6 times 6 is 36, and then I did 6 times 8 is 48i, and then 6 times -8 is -48i, then minus 8 squared I squared. And then when we simplify this, we just get 36 plus 64 equals 100. So, or we could do the short way. We know that A squared plus B squared is going to be the result we get when we multiply a complex number times its conjugate. So all I need to do is multiply the 6 times itself and add it to the 8 times itself. So 6 squared plus 8 squared is 100. So this is like a little shortcut that we can use when we're multiplying a complex number times its conjugate. If you can remember this shortcut, it makes it a little bit easier for you when you're trying to divide. So the next thing we're going to do is division. All right, so when given a quotient like A plus BI divided by C plus DI, we do not leave it in this form. Do you know why? Think about what I represents. I represents the square root of -1. You know that we do not leave a square root in the denominator when you are asked for the final rationalized answer. So we will multiply the fraction above by its complex conjugate of the denominator. This will take care of the root issue we are having in the denominator. Make sure you multiply the numerator and the denominator of the original fraction by the complex conjugate. Let's work this first one out. All right, so we have A plus BI divided by C plus DI, and I'm multiplying by the denominator's conjugate, which is C minus DI. I'm going to multiply the numerator and the denominator by this conjugate. And what I'm going to get is this result. All right, so in the numerator, we end up with AC minus ADI because we multiplied A times a negative DI, so I got negative ADI. And then I multiplied a BI times C, and I got plus BCI. And then I multiplied the BI times the negative DI, and I got negative BDI squared. And in the denominator, we get C squared plus D squared because we're using our little shortcut, okay? So whenever we multiply the complex number by its conjugate, this is what we're going to get. C squared plus D squared. Now, if you want to multiply that out the long way and see how the middle drops out, and then multiply D times D to get D squared, and then I times I is I squared, which is -1. And if you want to do all of those steps, then you go right ahead and knock yourself out. But if you can remember this shortcut, it's very easy and simple to remember, and it just makes it a little bit shorter to work out the problems. So C times C is C squared, D times D is D squared, and then you just put a plus in the middle, and that's it. All right, so in the next example, we're going to write the following quotients in standard form, meaning rationalized form. And so I'm going to work these out, and then actually I'm not going to do example 2. So let's just skip that example. Let's just skip that one. We're just going to do example 1. I'm going to write it out for you and then I'll explain. Okay, so let's take a look at what I've written here. First of all, I have multiplied this expression right here, this complex number expression, and I've multiplied the denominator by its conjugate. I've also multiplied the numerator by the same conjugate. So what I ended up with was 6 times 1 is 6, 6 times 2i is 12i, negative 7i times 1 is negative 7i, and then negative 7i times 2i is negative 14i squared. All over, and then the conjugate down here. When I multiply this complex number by its conjugate, I'm going to square this value, and then I'm going to add the square of this value. So 1 plus 2 squared is 4, so 1 plus 4. All right, then I need to simplify this. So I come down here and I wrote 6 plus 12i minus 7i is 5i, minus 14i squared is actually plus 14, because remember, I squared is negative 1. So this is like a negative 14 times a negative 1. And negative 14 times a negative 1 is a positive 14. So I wrote this positive 14 right here. Divided by, and then I just add the 1 and the 4, and I get a 5. Next, I'm going to combine like terms right here. Here I have a 6 and a 14 that I can add together. So I add the 6 and the 14 together, and I get 20 plus 5i. And there's my 5i. All over 5. All over 5. Now you see I've drawn these red lines through here. This means that I have reduced this because each one of these numbers is divisible by 5. So I'm able to reduce this fraction. So 5 goes into 5 once, 5 goes into 5 once, 5 goes into 20 4 times. So what I'm left with after I reduce this down is I'm just left with the 4 plus an I, 4 plus I. And this right here is my final answer. Okay, remember we're going to skip number 2. Just skip that one. All right, so on the next page we've got some complex numbers in standard form, and we want to write them in standard form. We have some radicals here that are negative under the radical, which means that they're complex numbers because they have an I, or they represent I. So we're going to rewrite these radical expressions as a complex number. So, and then we're going to multiply them together. So let's go ahead and do that. I'm going to expand this so you can see this a little bit easier. All right, so one of the things that I can do for number 1 is I can go ahead, since this is a multiplication, since we're multiplying these two radicals together, I can actually just multiply what's inside the radical together and then just take the square root. So this simplifies really easily. I can just take the square root of a negative 3 times a negative 12. Well, a negative 3 times a negative 12 is a positive 36. So really what we're doing is we're just taking the square root of 36, which is going to give us a plus or minus 6. And that's it. So this one was really easy to do. Now if I did it as a complex number, this is what it would look like. So it might look like this. I root 3 times I root 12. Well, I times I is I squared. And square root of 3 times square root of 12 is square root of 36. So here we end up with our negative 1. square root of 36, which is negative or plus or minus root 6. Anyway, you still get a plus or minus 6 for negative square root of 36. So either way you do this, you're going to get the same answer. Now in this example, we are subtracting these two radical expressions. And if you remember from Algebra 2, that you cannot combine two radical expressions that aren't like terms. So we have to get these two radical expressions into like terms first. So what we want to do is try to find what perfect squares we have inside these radicals. Well, I know that 48 can be broken down into some parts. So 48 divided by 24, 2, 2, 6, 2, 3, 16 times 3. All right, so the main thing I want you to remember about working with these kinds of expressions here, where you have something in parentheses squared, you always need to remember that whatever's inside the parentheses is being multiplied times itself. That's where the squared comes in. So make sure that when you're writing out your problem and you're trying to, you cannot distribute the squared. That's not how it works. You have to break this out. Okay, so we're going to multiply this -1 times this -1, and that's going to give us a +1. And then we're going to multiply this -1 times this root -3, and that's going to give us a minus root -3. And then we're going to do it again with the inside. Root -3 times the -1. That's going to give us another minus root -3. And then the last term is going to be root -3 times root -3. So we're going to get a plus root -3 squared. And then we're going to simplify. So I have a 1. I have a negative root -3 plus another negative root -3. So I have 2 of those. And I'm going to simplify this. Positive root -3 squared. Well, that's just a -3. So the next thing I'm going to do is combine like terms. So 1 minus 3 is -2. So I have a -2 minus 2 root -3, except I'm not going to leave that as a root -3. I'm going to rewrite that as a -2i root 3. And I'm going to leave my I in the middle between my number and my root, because I don't want my I to get stuck up underneath this radical symbol. I don't want that to happen. So I'm going to write it right here before the radical symbol so that it's clear that this I is pulled out of the radical and it's on the outside. Okay, now we're going to try to find the roots of the quadratic equation x squared plus 4 equals 0. So don't forget what the real square root of 4 is. All right, so I have used the traditional convention to solve for x, and I have subtracted 4 from each side of the equation, and I've gotten x squared equals a -4. And then I've taken the square root of each side to solve for x. And so when I take the square root of x squared, I get x. And when I take the square root of a -4, I get plus or minus the square root of -4. All right, so we can simplify this now that we know that we can use I to represent this negative sign that's inside the radical. So I'm going to rewrite this with an I. All right, so I've rewritten it as x equals plus or minus the square root of 4 is 2, and the square root of negative 1 is I. So square root of 4, 2, and square root of the negative 1, I. All right, in the next example, we're going to use the quadratic formula to help us solve for x. All right, so here I've put in all my parts of my quadratic formula. I have identified a, b, and c. A is 3, b is negative 2, and c is 5. And I have plugged those into my quadratic formula. Negative b, negative 2, plus or minus b squared, negative 2. Notice that I'm using parentheses, minus 4 times 3, which is a, times 5, which is c, all over 2 times a, which is 3. So 2 times 3. Make sure that you've got your a, b's, and c's all in the right places in your formula. Make sure that you haven't stuck any x's in here. X's do not belong inside the formula. X goes over here. This is x. We're solving for x, so we're not going to be putting x's in here, okay? And then we're going to simplify. Okay, so the first simplification I did was to find out what I had right in here inside my discriminant. If you remember from quadratics, that's what this is called. This is called the discriminant, so I want to find out what this number is. So I found out that negative 2 squared is 4 minus 60. 4 minus 60 is a negative 56. So now I know I'm going to have an imaginary number because I've got a square root of negative. So square root of negative is going to give me an imaginary number. Okay, so I have broken down my negative 56 into 4 times 14 times a negative 1. I tried to find the factors of 56 that make perfect squares, and I found that 56 is divisible by 4. So 4 times 14 gives me 56. Then I'm going to simplify again, and I'm going to get x is equal to 2 plus or minus. Now I'm going to take the square root of 4, which is 2. I'm also going to take out this negative 1, square root of negative 1, which is I. And I'm going to be left with root 14. And I can't simplify that root 14 anymore because that's as far as I can go with that. All over 6. Okay, so I can reduce this since each one of these numbers is divisible by 2. I can reduce this by 2. So I'm going to reduce this 2 to 1. I'm going to reduce this 2 to 1. And I'm going to reduce this 6 to 3. So my final answer is going to be 1 plus I root 14 over, with my 14 in there, over 3, and 1 minus I root 14 over 3. And that's my final answer. Those are the two roots. Those are the two solutions for x using the quadratic formula.